Okay, hello guys, today I'm gonna solve LeetCode problem 2421, number of good paths. We are given n nodes from 0 to n minus 1, so in this case n equals to 0, and the nodes are numbered from 0 to 4. And also each node will have a corresponding value to it, so in this example, node 1 has a value of 3, node 0 has a value of 1. We are going to find a good path, which is gonna be the path that has the same starting and ending value. So in this case, they are having the same value of 3. And also, each value in between the path must be less than the starting or the ending value. So in this case, 1 is less than 3, 2 is less than 3. So this is a good path. Also, each individual node can be counted as a path. So in this example, we have 5 nodes for 5 paths, plus the path we found earlier for a total of 6. That's why we output 6 here. So to solve this problem, we're going to utilize a data structure called union find. There are many tutorials online for this data structure, you can look it up, but I'm going to touch briefly about this data structure in this tutorial. So I'm going to use this graph as an example. First, we want to create a hash map that maps the value with the corresponding nodes. So in this case, for value 1, we are mapping node 0 and node 3. For value 2, we are mapping node 2, and for value 3, we are mapping node 1 and node 4. After creating the hash map, you want to iterate each key, but notice that I have sorted the key in increasing order because we want to start at a path that has the smallest starting and ending value. Let's say we start at path 33. In this path, there might be a sub-problem for path 22, and for path 22, there also might be a sub-problem for path 11. That's why we want to work our way up from the bottom, and as we're increasing the value, we're also increasing the count. This process will make it easier for us to counting the number of good paths. So for iteration 1, I'm going to start at value 1, and for each value, I'm going to iterate the list of nodes. So in this case, let's start with node 0. For each node, I'm going to look at its neighbor. For node 0, it's going to be 1 and 2. And I'm going to check the neighbor's value, and if the neighbor's value is smaller than the current node's value, I'm going to union these two together. But in this case, neighbor 1 has a value of 3 greater than the current node's value, which is 1. That's why I'm not doing anything. So our current union find is going to be 0, 1. Now I'm going to moving on to node 3. For node 3, I'm going to check its neighbor. It's going to be neighbor 2. Again, neighbor 2 has a value of 2 greater than the current node value of 1, so I'm not doing anything. I'm just gonna add the current node 3 to the union find data structure. After I finish traversing the list of nodes, I'm gonna make a count table. This table basically counts the number of good paths in this current iteration. So for iteration 1, I'm adding node 0 and node 3 to the union find data structure. So remember when I say earlier that each individual node can be counted as a good path. So node 0 has 1 good path and node 3 also have 1 good path for the total of 2. So our current output result is going to be 2. Moving on to value 2, this value only have 1 node, which is node 2. Again, we're going to check its neighbor. First, neighbor 0 has the value of 1, which is smaller than the current value of 2. So we union 0 and 2 together just like this. Now moving on to neighbor 3. It has a value of 1, which is also smaller than the current value of 2, so we're going to union 2 and 3 together. You might be wondering why we are making this connection between 0 and 3, but not a connection between 2 and 3 like this graph, because we are implementing the path compression of union find data structure. Basically, we don't want to make a linked list in this data structure, because if we want to call the operation find, say 3, we have to traverse 2 nodes, but if we are adding to the root directly like this, if we call find 3, it only traverses 1 node instead of 2 like this. I forgot to talk about neighbor 4 of 2, but we don't add 4 because its value 3 is greater than 2. So sorry about that. Anyway, after the second iteration, the data structure is going to be like this. Now what we're going to do is update the count table of this current iteration. Notice that we only do 1 union operation for node 2, so the current result is going to be 2 plus 1 equals 3, just like this. We are updating the count of node 0 because find 2 will return the root of 2, which is going to be 0. Now moving on to iteration 3, I'm going to explain in more detail why we're using this count table, so bear with me. For value 3, we start at node 1. Node 1 has neighbor 0. Neighbor 0 has a value of 1, which is smaller than the current value of 3, so we union 0 and 1. Moving on to node 4. Node 4 has a neighbor of 2, and neighbor 2 also has a value of 2, which is smaller than the current value of 3. So we union 2 and 4. So this is our final union and find data structure. And now I'm going to talk a little bit about why we're using this count table. For this iteration, we're adding 2 nodes, node 1 and node 4. So each node can be counted as an individual path. So we're having 2 paths already. And the final path is going to be the path between these 2 nodes. So we have a total of 3 good paths in this iteration. So the way this counting table works is that for each node we are iterating, we're going to find the root of that node. So in this case, find 1 will return 0. As you can see here, node 1 has a root of 0. And we're going to update that root accordingly. So node 0, in this case, we have a count of 1. And we're going to add that count to the current result. So 3 plus 1. Now moving on to node 4, again we're finding the root of node 4, which is also going to be 0. As you can see here, node 4 has the root of 0. So again, we're incrementing the count of root 0 to 2 and add it to the result. As you can see here, we have obtained the value of 3 like we did earlier by using this count table. Okay, since we have iterated all of the keys in this hash map, our algorithm is finished and the final result is going to be 6. But I'm going to touch more on the counting table. Now suppose for this iteration, we union another node of 7. So we union 3 nodes in total. Let's see how many good paths we can make. First, it's going to be 3 individual nodes, right? And then the path 1, 4 like we did. Another path from 7 and 1. And finally, the path from 7 to 4 for a total of 6 paths. So in general, for n nodes, the total number of good paths is going to be 1 plus 2 plus 3 to the n. Like in this case, n equals 3. So it's going to be 1 plus 2 plus 3, which is equals 6. Now let's see how this counting table is used if we have node 7 in the union and find data structure. And also I'm going to update node 7 here in the list of nodes. Again, we start at node 1. We're going to find the root of node 1, which is going to be 0. And we're going to update the count of 0 accordingly. And as we're updating, we're going to add this count back to our result. So our result earlier is going to be 3, and we add 1 here. Now moving on to node 4, we do the same thing. We're finding the root of node 4, which is also going to be 0. So we're updating the count of 0 to 2 and add to the current result. And finally, we're going to find the root of node 7, which is also going to be 0. So we update accordingly again and add to the final result. As you can see, we have 6 good paths in this iteration, if we're including node 7, and that is the same as using the formula I just talked about earlier when n equals 3, which is gonna be 6 also. So this counting table works perfectly, and that's basically the whole algorithm. Now we're gonna move on to the coding section. Okay, first I'm gonna implement the union find class. And before I do anything, I just want to say that I will not go into super detail on how this data structure works. If you have trouble understanding it, you can look up other tutorial online. One source I recommended is going to be LeetCode. I think he has really good explanation on this topic, and he also helped me understand this problem. So yeah, definitely check him out if you have trouble understanding the union find. But anyway, I'm just going to go briefly on how I do it. First, we're going to pass in n, which is going to be the total number of nodes in the graph we are working at, and we initialize the parent array to be the length of n. And after the instruction, the parent array should look something like this. Say we have n equals to 5. This is how the parent array looks. And then we're going to make another array called rank. I'm going to explain a little bit later why we do this. But now let's move on to the find operation, which is going to take a node and return the root of that node. So while the parent of node is not equal to node, which means that we have not reached the root of this node yet, we're going to first do the path compression I talked about earlier. Again, this is a little bit complex, so if you have trouble understanding it, definitely look up tutorial online first. But anyway, after that, we're going to make the node to be the parent. That's how we traverse up the tree and reach the root. And after we have reached the root, we just simply return it. For the union function, we're going to take 2 nodes, node 1 and node 2, and we're basically going to union these two nodes together. So first, we're going to find the root of these two nodes using the find function I just created earlier. And I'm going to check if root 1 is equal to root 2. That means they are in the same set. So I basically don't have to union them and just return. If not, now I'm going to explain why we're using the rank array real quick. Okay, say we have root 1 and root 2. Root 1 has a structure that looks like this, and root 2 only has one node. So in this case, root 1 has a rank of 3, and root 2 has a rank of 1. So we want to union root 1 and root 2 in such a way so that the one with the lower rank will be union with the one with the higher rank. And why are we doing this? Let me show you what happened if we do union root 1 to root 2. In this case, if we do the find operation in this node, we have to jump 2 steps to reach the root. Whereas if we do normally, when we union root 2 to root 1, and we want to do find operation in this node, we only have to jump 1 step to reach the root. So that's why we want to use the rank array so that we can optimize the union function. So what I'm going to do is I'm going to check if rank of root 1 is greater than rank of root 2. If that is the case, basically I'm going to union root 2 to root 1 by making the parent of root 2 to be root 1. And also I have to increment the rank of root 1 by the rank of root 2 because I just add root 2 to root 1. And the else is basically the opposite, so I'm just going to copy this code real quick and paste here and change a little bit. I'm sorry guys, I realized that I forgot to add self here. It's a thing in Python, so if you follow along, I'm really sorry. I'm just going to leave the whole code in the description. But anyway, that's about it for the union find class. Now we're moving on to the solution. I'm just going to move this one down so that it's easier to see. Okay, so first we're going to create the adjacency list, which is basically a hash map where the key is going to be the node and the value is basically the neighbor of that node. And we're going to iterate this edge array they gave us. And we're going to map each node to that hash map. And we're going to do it both ways because this is the undirected. After that, we're going to make another hash map. This one is basically the value hash map we did in the explanation earlier. And we're going to iterate this valve array. So I just want to explain a little bit about this valves array. Basically, the I is the index of that valve and the val is the element of that index. So you can think of this as the I is the node and the val is the value associated with that node. So in this values hash map, remember what we did? We gonna map the key, which is the value, to the node, which is I. Yeah, so basically this is how this loop works. And after that, we're going to initialize the result output to be 0 and also an instant of union find. And we're going to initialize it with the length of valves, which is basically n. Now, like what we did in the explanation, we're going to traverse the key of the hash map values. So we do something like this. Remember, we have to sort it. Now, each key or each value, we have the list of nodes corresponding to that value, right? So we want to traverse that list. And for each node, we want to traverse each neighbor. So we're using the adjacency list we created earlier for that. And finally, we check if the neighbor values is less than or equal to the values of the current node. That's when we have to union these two nodes together. And now we're going to create another hash map, which is basically the count table we did in the explanation. And for every node that is corresponding to the current value we are at, remember what we did? We're going to find the root of that node and we basically going to increment that count by 1. And after increment the count that root, we basically just add it to the resolve. So that's what we did. I'll misspell this. Okay, just copy the whole thing and paste this here. And that is pretty much it. We just have to return or resolve. Oh my god, what happened here? I'm just gonna backspace a little bit. And that is the whole solution code. Now let's try to run it. Okay, as you can see, the code is accepted. Now we submit it and see. 1 second. Alright, thank you guys. If you have any question, please leave it down in the comment. If you like this video, please leave me a like and subscribe. And yeah, if you have any other suggestions, just leave it down in the comment. I'll read all of them. Thank you so much and see you guys next time.